NENOMATICA, where mathematics meets YouTube excellence. Let's look at our example. We have a system of two equations, x plus y equals 6, and x times y equals 4. We need to find the value of x cubed plus y cubed. Let's start our solution. First, we'll use an important algebraic identity to help us find x cubed plus y cubed. Now, we can substitute our known values into this formula. We know that x plus y equals 6, and x times y equals 4. Let's substitute these values into our expression. We've added 2xy minus 2xy, which equals 0, so the equation remains valid. This helps us rearrange the terms in a way that will be useful for our next steps. Now, we notice that x squared plus 2x, y plus y squared is the perfect square of x plus y. So we can further simplify our expression. Now, we can substitute the values from our system of equations. We know that x plus y equals 6, and x times y equals 4. Let's substitute these values. Let's calculate this step by step. 6 squared equals 36. 3 times 4 equals 12. 36 minus 12 equals 24. Finally, 6 times 24 equals 144. Therefore, x cubed plus y cubed equals 144. Let's summarize what we've learned in this problem. We started with a system of equations x plus y equals 6 and x times y equals 4. We used the cubic sum identity x cubed plus y cubed equals open parenthesis x plus y close parenthesis times open parenthesis x squared minus xy plus y squared close parenthesis. By substituting our known values and performing algebraic manipulations, we found that x cubed plus y cubed equals 144. This problem demonstrates how algebraic identities can be powerful tools for solving complex expressions without having to find the individual values of the variables. X plus y equals 6, and x squared plus y squared equals 40. We need to find the value of x to the power of 6 plus y to the power of 6. Let's start by using an algebraic identity. We know that the square of a sum equals the sum of squares plus twice the product of the terms. In other words, x plus y squared equals x squared plus 2xy plus y squared. In our problem, we know that x plus y equals 6, so x plus y squared equals 36. We also know that x squared plus y squared equals 40. Now, since x plus y equals 6, we can substitute this into our expanded expression. This gives us x plus y squared equals 40 plus 2xy. Since x plus y squared equals 36, we get 36 equals 40 plus 2xy. Let's solve for 2xy. 36 equals 40 plus 2xy. Subtracting 40 from both sides, we get 2xy equals negative 4. Dividing both sides by 2, we get xy equals negative 2. Now, we'll use another algebraic identity to calculate x cubed plus y cubed. The sum of cubes can be expressed as a plus b times a squared minus a times b plus b squared equals a cubed plus b cubed. In our problem, this becomes x plus y times x squared minus xy plus y squared. We know that x plus y equals 6, xy equals negative 2, and x squared plus y squared equals 40. So x cubed plus y cubed equals 6 times 40 minus negative 2, which equals 6 times 42, which equals 252. Now, we need to find x to the power of 6 plus y to the power of 6. We can use the following identity. The square of x cubed plus y cubed equals x to the power of 6 plus y to the power of 6 plus 2 times x cubed times y cubed. Rearranging, we get x to the power of 6 plus y to the power of 6 equals the square of x cubed plus y cubed minus 2 times x cubed times y cubed. We need to find x cubed times y cubed. We know that xy equals negative 2, so x cubed times y cubed equals negative 2 cubed, which is negative 8. Now we can substitute all our values. X to the power of 6 plus y to the power of 6 equals the square of 252 minus 2 times negative 8. Let's calculate the final answer. X to the power of 6 plus y to the power of 6 equals 252 squared plus 16. 252 squared equals 63,504. 63,504 plus 16 equals 63,520. Therefore, x to the power of 6 plus y to the power of 6 equals 63,520. Let's start with our example. We have an equation where x plus 1 over x equals a. Using this relationship, we need to find the value of x cubed plus 1 over x cubed. To solve this problem, we'll use an important factorization identity. The sum of cubes, a cube plus b cubed, can be factored as the product of a plus b times a squared minus a times b plus b squared. This will be crucial for our solution. Now, let's simplify this expression. First, we know that x plus 1 over x equals a. Let's focus on the bracket term x squared minus x times 1 over x plus 1 over x squared. We can simplify. The middle term x times 1 over x is just 1. Next, we'll use another algebraic identity. We know that a squared plus b squared equals the quantity a plus b squared minus 2ab. We'll apply this to rearrange our expression. Now, we'll focus on the term x squared plus 1 over x squared. Using our identity, we can express this as the quantity x plus 1 over x squared minus 2. And we know that x plus 1 over x equals a. So x plus 1 over x squared equals a squared. Let's simplify the constants inside the bracket. -2 minus 1 equals -3. Now, we can substitute our original equation. Since x plus 1 over x equals a, we get x cubed plus 1 over x cubed equals a times a squared minus 3. Finally, we can simplify this to x cubed plus 1 over x cubed equals a cubed minus 3a. Our example problem states, suppose x and y are two real numbers such that x cubed plus y cubed equals 133 and x plus y equals 7. Find the value of x times y. The first step in solving this problem is to use the algebraic identity for the sum of cubes. The sum of cubes, x cubed plus y cubed, can be factored as the sum of x plus y multiplied by the quantity x squared plus y squared minus x times y. Now, we'll substitute our given values into this identity. We know that x cubed plus y cubed equals 133 and x plus y equals 7. So we can write 133 equals 7 times the quantity x squared plus y squared minus x times y. Next, we'll divide both sides of the equation by 7. 133 divided by 7 is 19. So we get 19 equals x squared plus y squared minus x times y. Now, we'll use another algebraic identity. We know that x plus y squared equals x squared plus y squared plus 2 times x times y. We can rearrange this to express x squared plus y squared in terms of x plus y squared and x times y. Since we know that x plus y equals 7, we can say that x plus y squared equals 49. Let's substitute this value into our equation. Now, we'll solve for x times y. First, let's rearrange the equation. We subtract 49 from both sides, getting -30 equals -3 times xy. Finally, we'll divide both sides by -3. -30 divided by -3 is 10. Therefore, x times y equals 10. And there we have our answer. The value of x times y is 10. Let's summarize the key steps we took to solve this problem. Let's review what we've learned. We started with a system of equations where x cubed plus y cubed equals 133 and x plus y equals 7. Using the sum of cubes identity, we were able to introduce the variable x times y, which was what we needed to find. By applying algebraic manipulations and substituting known values, we determined that x times y equals 10. This problem demonstrates how algebraic identities can be powerful tools for solving complex equations. Let's look at the following example. We need to determine the value of the algebraic fraction 110 cubed plus 73 cubed divided by 110 cubed plus 37 cubed. Let's start by identifying some important values from the handwritten notes. We can see that a equals 73 and b equals 37, and a plus b equals 110. Let's recall an important algebraic identity that can help us. From the hint in the image, we can see that x cubed plus y cubed equals the product of x plus y, and x squared minus xy plus y squared. Now, let's apply this identity to our problem. In the numerator, we have 110 cubed plus 73 cubed. We can rewrite this using our identity. Since we know that a equals 73 and a plus b equals 110, we can substitute b equals 37. So 110 cubed plus 73 cubed equals, using our identity, the product of 110 plus 73 and 110 squared minus 110 times 73 plus 73 squared. Next, let's work on the denominator. In the denominator, we have 110 cubed plus 37 cubed. We can use the same identity. So 110 cubed plus 37 cubed equals the product of 110 plus 37 and 110 squared minus 110 times 37 plus 37 squared. We know that 110 plus 37 equals 147. Now, let's rewrite our original fraction using these expressions. The numerator is 183 times 110 squared minus 110 times 73 plus 73 squared. The denominator is 147 times 110 squared minus 110 times 37 plus 37 squared. Let's look at the expressions in the parentheses more carefully. Let's substitute a equals 73 and b equals 37 to see if we can find a pattern. In the numerator, we have 110 squared minus 110 times 73 plus 73 squared. We can substitute 110 with a plus b, which gives us a plus b squared minus a plus b times a plus a squared. This simplifies to a squared plus 2 a plus b squared minus a squared minus a plus a squared, which further simplifies to a squared plus b squared plus a. Similarly for the denominator, we have 110 squared minus 110 times 37 plus 37 squared. Again, substituting 110 with a plus b, we get a plus b squared minus a plus b times b plus b squared. This simplifies to a squared plus 2 a plus b squared minus a minus b squared plus b squared, which further simplifies to a squared plus a plus b squared. Now, we have an interesting result. The expressions in the parentheses in both the numerator and denominator are identical, a squared plus a plus b squared. So our fraction becomes 183 divided by 147. We can simplify this fraction. 183 divided by 147 equals 183 over 147. Welcome to our math video. Today, we'll be solving a system of equations to find how many real solution triples A, B, C satisfy this system. Let's start by checking a special case. What happens if C equals 0? If C equals 0, our system simplifies to a plus B equals 0, a squared plus B squared equals 0, and a cubed plus B cubed equals 0. Now, if a squared plus B squared equals 0, that means both A and B must be 0, since the sum of squares can only be 0 when each term is 0. So we found our first solution, a equals 0, B equals 0, and C equals 0. Now, let's use an algebraic identity to find more information. We know that a plus b squared equals a squared plus b squared plus 2ab. From our system, we know a plus b equals 3c and a squared plus b squared equals 5c. So we can replace these in our identity. 3c squared equals 5c plus 2ab. Simplifying, 9c squared equals 5c plus 2ab. Now we can solve for ab. ab equals 9c squared minus 5c. All divided by 2. Let's use another identity to get a different expression for AB. We know that a cubed plus B cubed equals a plus B times a squared minus AB plus B squared. We substitute a plus B equals 3C and a cubed plus B cubed equals 9C. 3C times a squared minus AB plus B squared equals 9C. Dividing both sides by 3C, we get a squared minus AB plus B squared equals 3. But we know a squared plus b squared equals 5c, so 5c minus ab equals 3. Solving for ab equals 5c minus 3. Now, we have two different expressions for ab. We can set them equal to each other. 9c squared minus 5c over 2 equals 5c minus 3. Multiply both sides by 2. 9c squared minus 5c equals 10c minus 6. Rearranging, 9c squared minus 15c plus 6 equals 0. Dividing by 3. 3c squared minus 5c plus 2 equals 0. We can factor this. 3c minus 2 times c minus 1 equals 0. So either c equals 2/3 or c equals 1. Let's analyze the case where c equals 1. When c equals 1, we have a plus b equals 3, and ab equals 5 times 1 minus 3, which equals 2. So we need to find two numbers that sum to 3 and multiply to 2. We can use the quadratic formula. If we call one of the numbers t, we get the equation t squared minus 3t plus 2 equals 0. This factors as t minus 1 times t minus 2 equals 0. So t equals 1 or t equals 2. Therefore, either it equals 1 and b equals 2, or it equals 2 and b equals 1. This gives us two more solutions. It equals 1, b equals 2, c equals 1, or it equals 2, b equals 1, c equals 1. Now, let's handle the case where c equals 2/3. When c equals 2/3, we have a plus b equals 3 times 2/3, which equals 2, and ab equals 5 times 2/3 minus 3, which equals 5/3 minus 3, which equals negative 1/3. So we need two numbers that sum to 2 and multiply to negative 1/3. Again, using the quadratic approach, if one number is t, we get t squared minus 2t plus 1/3 equals 0. Using the quadratic formula, t equals 2 plus or minus the square root of 4 minus 4/3, all divided by 2. This simplifies to t equals 1 plus or minus the square root of 2/3. So we get two more solutions. A equals 1 plus the square root of 2/3, b equals 1 minus the square root of 2/3, c equals 2/3, or a and b switched. Now, let's count all the solutions we've found. We found one solution when c equals 0. A equals 0, b equals 0, c equals 0. We found two solutions when c equals 1. A equals 1, b equals 2, c equals 1, or a equals 2, b equals 1, c equals 1. And we found two solutions when c equals 2/3, involving square roots. So in total, we have 5 different real solution triples, a, b, c, that satisfy our system of equations. Let's summarize what we've learned. We started by checking the special case where c equals 0, which gave us one solution. We then used algebraic identities to derive two different expressions for the product AB. By setting these expressions equal, we found that c must equal either 1 or 2/3. For each of these c values, we found the corresponding pairs of a and b values. This approach of finding constraints and solving for variables is a powerful technique for tackling systems of equations with multiple unknowns. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.